Today we will be starting with self-induction. Mainly, I'm going to solve the GS sessions because it was asked more for the grade 12 GS. Okay, so let's start, but I'm going to write a small note before that. If you watched the capacitors with me before, you can remember that I told you we have three main things in electricity, which is the voltage, the current, and the charge. Okay, our main focus in self-induction is about the current. Okay, so we will be talking about the current first. Second, you have a few physical quantities you have to work on. The first one, it's the magnetic flux. Magnetic flux, it's phi equals to Li. And you have to focus on the EMF, which is the electromotive force, or what we used to call in grade 10 voltage or ideal voltage. Okay, and it is represented by E, small e, and its formula, it's minus d flux over dt. And when I say flux, I already mentioned that it's Li. So instead of this, instead of the flux, I will be putting, instead of the flux, phi Li. Okay, so it's, and since L is a constant, as we said about the capacitor, C is a constant, so we keep it outside the derivative. Same thing for the inductance. L is called the inductance. It's one of the main characteristics of the coil that we're working on. So it's minus L di over dt. So now we have one formula, two formulas. The second one is the most important one. Okay, and this is what we call Faraday's law, by the way. Faraday's law. Okay. Now, as we're working on I, they're supposed to ask you about the differential equation, about the solution, and all of that. You have to expect that. Okay. And as we said in the capacitor, if you watch the capacitor, if you don't, I'm repeating from scratch. We start with the law of addition of voltages for the current, the circuit that we have, addition of voltages. For example, in our circuit here, in this session, we have the left part, which is the generator and the coil, and the component V1, which is the resistor in our problem. And we have the right side, which is only the coil with another resistor. So it's just like the capacitor, same type of figure, same type of problems. It's not supposed to be hard. Okay, now, if I have anything in mind when I'm solving, I will re-add some notes. Okay, now, let's forget about the notes for a little bit now. We have, in this problem, a generator of ideal voltage E equals to 9. Okay. We have D1 of resistance R1, and we have D2 of resistance R2, and we have a coil of inductance L equals 1 Henry. Okay, in case you don't know the unit. Now we have K is a double switch. We can put it on the left side or on the right. Now, if we place the switch on the right, on the left side at position 1, we're just working on the left side of the circuit, so we leave D2 behind now. Okay, at instant T, the circuit carries a current I1. So at the beginning, we didn't have a current. Once we put the switch and we function the generator, we will have at some instant a current I1 that is flowing from the generator along the resistor and the coil. Okay, now one thing you have to know about the coil, it opposes everything that it gets. If it gets an increasing current over time, it will work in a way to decrease this current, to decrease the increase of the current. Okay, so it always works in the opposite way. Now, you tell me, so if we don't have a generator, that means it helps? Yes. If the current is increasing, the coil works to decrease that value or that function. Now, when we don't have a generator, when we cut the generator, the coil will try its best to keep the current on flowing. It doesn't want it to disappear. So it always works in the opposite way. Now, In question 1, they're asking us to derive the differential equation in I1. As expected, just like we do in the capacitor, we're doing the same here. So if you're familiar with the capacitor, you're supposed to like this chapter. It's the same steps of calculation, even though it's a different physics concept. Now, we start always step 1 by the law of additional voltages, or what you're supposed to know as Kirchhoff's law. Okay. What do we have in our case? We have the generator, and it's giving out to D1 plus the coil. Okay. Now, as I mentioned before, the voltage of the generator, it's E, the ideal voltage, minus Ri, with R being the internal resistance. Mainly, they don't give internal resistance, so we remove that part and we only end up with E. Now, about the resistor, UD, it's equal to Ri, using Ohm's law. This is everything we know about the resistor. Okay, so we already have I in this expression, so everything is okay. Now UL, its formula is Ri minus E. If the current is flowing in, let's suppose we have point A and point B, they mentioned that. Point A and point D, excuse me, we have the current I1 flowing through A and going out from D. So UAD of the coil, it's supposed to be Ri minus E. Now, if we take the opposite direction, as we always talked about that in 10 and 11, UDA, you took the opposite sense of the current, so you have to say E minus Ri. So it's the conventional direction that we choose. Okay, now Ri minus E, and we already mentioned E in the notes. E, it's minus L di over dt. And by the way, E equals minus L di over dt. What does it mean? If we have an increase in the current, the derivative of an increasing function should be positive always. And L is also positive always. So if L is positive and di over dt is positive in this case because the current is increasing, the whole function with the negative sign before it should be negative. Positive and positive, it's positive. And we have a minus in the formula, so it will become negative. Okay, so what does that mean? When the current is increasing, okay, E will be negative. It will be working in the opposite direction. Okay, now, when the current decreases, so you have to understand the meaning of the formula, not only write it. So if the current is decreasing, then di over dt should be negative. Decreasing function, negative direction. And L is always positive. Now, the formula E minus L di over dt, the whole thing, di over dt is negative. L is positive, and with a negative sign in the formula, so we have minus, plus, and minus. Together, they should give a positive value. Okay, so here, the coil is supposed to be working with the direction of the current, so it can help it increase because it's decreasing in the absence of a generator. So the formula is really important to be understood. Okay, so in case we have an increase in the current because of the generator connected across the coil will behave in the opposite way and create an EMF that is negative to oppose that increase. This is what we have a coil that is behaving as a generator in opposition. It's not helping, it's opposing. Now, about the second method, when we have decrease in the current, E is positive, it's helping the current, it's pushing the current in the same direction to keep it functioning, to keep it moving. So here we have an actual generator that is helping. So we have to be careful with the signs, with the decrease, with the increase, so we can know if we have a generator or not. Okay, now let's go back to what we're doing. Okay, so we have UL, it's Ri minus E. E is considered the voltage. So we don't want the voltage in our expression. We have to replace it by something else concerning the current because it's differential equation for I. So Ri minus E, I will replace E here and will put instead of it its formula. So the whole thing will be Ri plus LdI over dt. So now I got the voltage of QL in function of I. I have the resistor in function of I, and I have the battery that has a constant value for the voltage of it. Okay, now, was there something that I have to mention here? No, I don't think so. So we will continue. I'll go back to my law of additional voltages. I will write E equals UD1 Ri plus UL, it's Ri plus LdI over dt. Now, one thing that I have to notice, which is Ri, the internal resistance, the small Ri, the internal resistance of the coil. Mainly, especially for LS, they give it 0. So I have to go back to my given and make sure that everything is clear and I'm not just adding random variables that are not supposed to be here. So we have negligible resistance for the coil. So we can remove the small r. Okay, that's when I remove the small r and I only end up with LdI over dt, and that's even better and easier. So I will remove. So E equals Ri plus LdI over dt. And once I see a derivative of a variable and the variable itself, I know that I got my differential equation and then stop. If they force you to find a specific way or a specific form of the differential equation, of course, you have to get to that form. If they don't, you can stop here. Sometimes they ask you to find di over dt by itself, no coefficient next to it. The coefficient next to the I over dt is L. That's when you have to divide the whole thing by L, so you can get E over L, R over Li, plus di over dt, so you can keep the derivative by itself. And that's even better. Okay, now we're done with the first question. Second question, verify that I1 is a solution of the preceding differential equation. Okay, so this question is really easy. Sometimes they ask you to verify that this is the solution. Sometimes they ask you to find tau. They give you the solution as this form, A1 minus E minus T over tau. Okay, and they ask you to find A and tau. What are they? What are they supposed to be in function of E and R1 and L? Okay, so these two questions are typically the same, just asking that in two different tones or two different ways. Okay, what are you supposed to do in these cases? You're supposed to write first the solution in front of you. Okay, if you're good with math and the parentheses, and you don't confuse how to continue your calculation, that's great. If you are struggling with math and to some extent, I prefer if you expand the solution that you have first. So you will get E over R1 times 1 and times the exponential that we have here. So we will get E over R1 minus E over R1 exponential of minus R1 over L T. Once you expand and you get rid of the parentheses and the over calculation, that's better for you, especially if you're nervous in the tests. Now, this is the first step for these types of questions. The second step, you have to find the derivative. Now, you're asking why? Because if I want to know, let's say you have a quadratic equation, okay, and I tell you, prove that x is equal to 2 is a solution of this equation. What do? You replace x by 2. I'm sorry, minus 4 here should be. So 2 squared minus 4 times 2 plus 4. So you get 4 minus 8 plus 4, which is 0, and you know it's a solution. Same thing here. It's a little bit more complicated than just x equals to 2. Now I have a whole expression for the solution. So my x in math, here it's I1. And my function here in math, it's the differential equation that I got in the previous solution, in the previous question. Okay, so it's a little bit hard here. If you understand the steps and you follow them and you remind yourself of them, it will be really easy. So the second step, I want the I over dt. Why? Because my function, which is the differential equation here, has two things, I and di over dt. So we have to be careful. We have to find both of them, the expression of both of them. Now I got I1, I first half of the problem. Now I need the derivative. Now let me write the derivative under the expression so we can make things clear. The derivative of a constant, E is a constant. Its value doesn't change. And the resistance also doesn't change because I have one resistance and resistor in the circuit. So why would it change? And I'm not changing it. I'm not changing its value. It's not a rheostat. I'm not taking off this resistor and putting something else. So it's a constant. Now the derivative of the constant by itself should be 0. Okay, now if you're good with the exponential in this here, you're not supposed to struggle in that. If you're not, just rewrite everything that you already have in your expression. So I rewrote E over R1 and the exponential, and I just put in the middle, in between them, a parenthesis, and I put whatever next to T on the line. Okay? So to make things less complicated, I will remove the parentheses and I will multiply everything. Minus and minus, they will become positive. E times R1 over R1 times L, E minus R1 over LT, and R1, we can simplify them. So simply, I got my derivative. If it's easy for you to solve it in just 2 steps, you can. If you struggle or you're nervous when you're presenting your tests, it's preferable you go step by step. Now I have my solution and I have its derivative. I take them and I replace them. So I replace I1 and di1 over dt in the differential equation. So I will write the differential equation, which is E over L equals, I just got it here in question 1, E over L, R over L, I di over dt, and it's R1, by the way. I just called it R. It's R1. Okay, so R1 over L I plus di over dt, and now I will replace this value here and this value here, and I think it should be easy if you decompose this into steps. So R1 over L, now instead of I will be putting E over R1, 1 minus E minus L over R1. R1 over L. Now let me put the expanded form. Minus E over R1, E minus R1 over L T. So we replace the first I. Now I need to replace the derivative, which is plus, and now the derivative, I just got it here. It's E over L, E minus R1 over L T. And that's it. Now I get rid of the parentheses. I will expand. And for the second term here, I don't have anything before the parentheses, so I simply just remove it. Remove the parentheses. So R1L E over R1. This is the first multiplication. The second is R1L E over R1. E minus R1 over LT plus E over L. This just stays the same. Okay. Now I'm supposed to get 0, just like the quadratic equation. When I replace with the solution, I'm supposed to get the 0. I'm expecting that. So now what do I have here? I have R1, 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 R1. They can be cancelled. If you notice, we have here E over L only. And on the left side, I also have E over L, so I can remove them. Now, R1 and R1, we get rid of them. we have E over L exponential of minus R1 over LT. And we have a negative sign before that expression. Here I have the same exact expression, E over L, E minus R1 over LT, but with the positive sign before it. So I have two same expression, just different signs, so we can remove them. And I will get 0 equals to 0 verified. Okay, so this is really the solution for the differential equation. Okay, now 3. Find in the steady state, the word steady state, it's a key word here. Steady state, that means I'm in my constant phase, nothing is changing, or the current specifically, it's not changing. So what does the word constant mean? When I say constant, that means I have a specific number. And this specific number, every time I find its derivative, it should be 0. So everything concerning di1 over dt should be removed. Okay, so the expression of the current I0 in terms of E and R1. Now, obviously, in my solution, in the previous question, I1, I don't have a derivative in the first place. Okay, so preferably we use the differential equation because it has I and it has di over dt. And my main goal is to use di over dt because they specifically said steady state. So this word steady state, I have to benefit from it. And the only way I can benefit from it is by rewriting the differential equation because it has di over dt. Now, since we have a steady state, okay, that means the current I that I write it a small I, now it's a constant. It has one value that is not changing. And in physics, when we have a physical quantity that is not changing anymore, we name it capital by a capital letter. So instead of I1, I will simply call it I. If they want it specifically, if they want you to specifically name it a specific name, like here, the current I0, okay, أكيد we prefer you write the letters that they want. So I1, it will become capital I0 because it's a constant at the steady phase. And di1 over dt, it's simply 0 because it's a constant and the derivative of a constant is simply 0. Now I replace that in the differential equation. I will get E over L, both of them are constants, R1 over L, both of them constants, and instead of I1, I will be putting I0, the constant form, the capital form. Okay, plus di1 over dt, which is 0, so plus 0, you don't have to write anything. Okay, now get I0 to one side. Obviously, everything is multiplied, and you have L on both sides, you can remove them. So I0, it will become, we take R1 to the other side, I0 will be E over R1. As expected, the current is the voltage over the resistance when we are talking about the steady phase. Okay. Now calculate in 3B, calculate I0. So I'm supposed to have like a value for E and R1. Okay, so I go back to my given. Do I have values for E and R1? Of course, I have E, it's 9, and I have R1, it's 90. So I benefit from them, so I can get the current at the steady phase, at its maximum phase. So I0 equals E over R1, already got, which is 9 volts over 90. So I0 is supposed to be 0.1 ampere. And that's a fine value. Now, in the second part, we have now the decay of the current in the component R2L and illumination of a lamp. Now we're placing the switch, the double switch on position 2. So we're getting rid of D1 and the generator. We only want the coil and the lamp, which is behaving as a resistor. Okay? So at an instant t, the circuit carries thus a current I2. Determine the direction of this current. Now, I don't want you to confuse this the coil is always opposing the change. And since we're cutting off the battery, so the current is decreasing. If the current is decreasing, then the coil will help it move even better in the previous direction it had. So let me explain that even clearer. When I had K on position 1, my current I1 was flowing out from the battery into the coil in this direction from A to D. When we cut off the generator suddenly and we replace the switch on position 2, now I don't have a generator, so the current is decreasing. But the coil still has one job, is to oppose what's happening to the current. So since the current is decreasing in value, but it's still going in the same direction, which is from A to D, the coil will try to help it move even better from A to D. Okay, so it doesn't change its direction. It continues in the same direction with the help of the coil. Okay, so determine the direction of this current. The current I2 has the same direction as I1. Okay, now derive the differential equation in I2. That's really easy, I suppose. We said that the first step we write the law of addition of voltages, and we start. What do we say? We say U of the coil. Now we have the switch on position 2, and instead of I1, we will be having I2, and the left side of the circuit will be avoided, and this I2 will keep on flowing through the lamp, or the lamp that is behaving as a resistor. Okay. Now, as we can see, we have U of the coil plus U of the lamp. Both of them are L. So let me just call UL plus UR, or UR2 or UD2, whatever you want. Just don't confuse these values. Instead of saying it's equal to the battery's voltage, we simply say 0. Because as the current is flowing from A to D, as I already know in the previous part. Okay, so same direction of the current, same everything. We just say UL plus UR2 equals to nothing. There's no generator, so 0. And at some point the current will stop, but the coil is trying to help it a little bit more before shutting down. Now UL still or I minus E. Why? Because the current is still flowing from A to D. I suppose it's D. Yeah. Okay, so UAD, it's still or I minus E. The current is still flowing in the same direction. I don't have a problem. Now UR2, it's the resistor 2, which is R2I. Okay, and now as we said, E is equal to minus LDI over dt. Now, some of you might ask, in the capacitor, we usually say I it's equal to plus dq over dt in the case of charge, or minus in the case of discharge. Why here we're not changing the sign with the change of what's happening in the circuit? Because the change that is happening in the circuit is happening in di over dt. When we're having a generator and the current is increasing, the increase is happening here in di over dt. And when we have the other way around, when we have a decrease and when we cut off the generator, the decrease is happening in di over dt. So if the sign is changing with di over dt, I don't have to change anything in the formula. Okay? I don't touch the formula if the change is happening in one of the physical quantities that I have. Okay? Now, instead of E, RI2 minus E, instead of E, I will put its expression, which is minus LDI over dt, which is RI2 plus LDI2 over dt. And this is my expression for the coil as always. Don't confuse it. We always get this. Okay, so they don't play with the conventional direction and what's happening. So mostly expect this answer. Now, UL, it's RI 2 plus LDI over dt. And as I said before, The coil doesn't have internal resistance, so simply we can remove the R, the small r, the coil UR, UL, it's Ri minus E, and it doesn't have an internal resistance in the given, it's in the given. So, and plus U R2, it's the resistor. We use Ohm's law as always. Okay, and you can divide the whole thing by L, so you can get the derivative by itself. So di2 over dt plus R2 over L I2. Okay, why do we have two currents? Because we have a decay and we have a generator. So we're supposing we have different currents, and that's it. This is the differential equation. It's not equal to E over L as expected because E is coming from the battery. In the previous part, we had the same value, but equals to E over L. E is coming from the battery, so that's expected to have 0 here. Okay, so this is question 1. Question 2. Now, question 1, the solution of this differential equation is I2 alpha E minus beta T. Show that alpha is equal to I0 and beta it's R2 over L. That's really easy. I told you in the previous part, every time they ask you about the constants, the coefficients next to the time and the exponential, it's like they're asking you to verify. It's the same type of solution for different questions. So that's really easy by now. Okay, so the first step we do, as I said before, we write the solution in front of us, which is I2 equals to alpha E minus beta T. This is the first step. The second step, we find its derivative, which is alpha E minus beta T. We keep them as they are, and we multiply in the middle by what's next to T, which is minus beta. And then we multiply the whole things by each other. We will get, of course, the negative sign should be at the beginning because everything is multiplied. Minus alpha beta E minus beta T. And this is the derivative. Now I tell them that I have to replace them. Replace I2 and di2 over dt into the differential equation. That's supposed to be really easy by now. Instead of proving that we have 0 equals 0, we simply just say that we solve the same thing, but we just have to get that alpha is equal to something and beta is equal to something. So the differential equation, it's di2 over dt, yes, plus R2 over L I2. So di2 over dt plus R2 over L I2. Now we replace them. The first is the derivative, which is minus alpha beta E minus beta T. I didn't put a parentheses like I always do because I don't have anything before the I2 over dt, so it will stay the same. Plus R2 over L, the constants. I2, it's alpha E minus beta T. And the whole thing, it's equal to 0. Now, I remove the parentheses. This is the second step. The third step. So minus alpha beta E minus beta T plus multiply the whole thing, you will get R2 alpha over L E minus beta T equals to 0. Now here, it's a little bit different than verifying, which we had in the first part. Here you have to take the exponential as a common factor. Once you get this, always remember E has to be taken as a common factor. So we have here and here two terms that have exponential. If we took the exponential as a common factor, from the first term we will have minus alpha beta, and from the second term we will be having R2 alpha over L, and don't forget the signs, by the way. Some people just put positive signs. They forget that some expressions have minus before them. Okay. Now what do we get at the end? The term that we have here equals to 0 because the exponential can never be 0. So how am I getting an expression equal to 0? Of course, it's not because of the exponential, it's because of the the factor next to the expression, next to the exponential. So minus alpha beta plus R2 alpha over L equals to 0. Take each one of them on the side. You will get minus R2 alpha over L. Now, before I continue, I cannot not notice that I have minus on both sides and I have alpha on both sides. So I will get that beta, it's equal to R2 over L, as they said, and as expected, it's always like this, okay? So, but you tell me I still have one thing that is missing, which is alpha. If you solve the whole thing and there's something still missing, you didn't get it, the last thing you're supposed to do is say, using the condition, the initial condition. What do I mean by that? When I use the time t0 equals 0, that thing opens to me a lot of values that I don't know. So using the initial conditions, by initial conditions, I mean when the time was 0. And I rewrite my solution, which is I2 equals, let me just make sure, there it is, it's alpha E minus beta T. So it's alpha E minus beta T. My problem is not with beta, I already know beta. It's E minus R2 over L T. Now my problem is with alpha, so I'm using the initial conditions. Now I ask myself, what was, when I write this expression, listen to my sentence carefully, this is what I mean. What was I2 when I put parentheses, I mean, I have a specific condition when T0 was equal to 0. At the beginning of the discharge, let me say, when we cut off the generator, the current was at its maximum, it was at its peak. Because when we have a generator, we will increase the current till it reaches a stable phase, which is the maximum phase. So when I decrease this current, I'm decreasing it from its maximum value. Okay, so I2 simply was I0, which is the value that I know at the beginning. It was at its peak. So instead of I2, I will put I0 because at the beginning of the experiment, I2 was the biggest value possible. And I will replace the time that I have in my expression with 0. But R2 times 0, the whole thing here will be 0. So I0 equals alpha E minus 0. And we all know that the exponential of 0 is 1. So simply alpha is I0. And what does I0 mean? Maximum value of the current at the beginning of the experiment. And which experiment do I mean? I don't mean when I started charging or when I started applying a current when I connected the generator to the battery, the generator to the coil. I mean maximum value of the current at the beginning of the experiment, the second experiment when I cut the generator. Because if you notice in the questions here, okay, I have in the first part, I have I, which is the first part, growth of the current. So in the first part, خلاص, I grew the current and it got to its maximum value. Now in the second part, we have the decay. So I started decreasing. This is a second experiment. I reset the clock and I redo my experiment where I'm decreasing the current from its peak, from its max. Okay, this is why I'm saying it's max. At the beginning of the experiment, when we just cut off the generator. And at the end, of course, it will be 0. But I'm taking T0 equals 0. I mean, at first, at just the beginning, when I cut off the generator and the current was max. So I got alpha, I got I0, and I already know that I0 from the previous part, it's E over R1, which is 0.1 ampere. Now you ask me, why are you using the previous part? You're doing another experiment. Yes, but in the first experiment, my current got to its peak, which is 0.1, and from there it started to decrease. So the beginning of my second experiment is the final point or the final time of my first experiment. So I, at the beginning of the second experiment, is the same as I0 at the first experiment. Okay, it's the same. So I finished my first experiment, I got my maximum I, and from there I started my second experiment and I decreased I from there all the way down to 0. Now this is it as expected. Okay, and it's really important to understand what's happening physically so you can know how to answer the questions. Sometimes memorizing just formulas cannot help. Now, part B, duration of illumination of a lamp. The resistor D2, we have R2, it's 400. This lamp gives light as long as the current it carries is not less than 20 milliampere, which is divided by 1000, it's 0.02 ampere. Show that the lamp gives light at the instant when the circuit is closed. Just when we close the switch on position 2, I will re-say it. The coil was connected to the generator and it reached a steady phase where the current was at its peak. The current at the end of the first phase was I0 equals 0.1 ampere. When I started my second experiment and I switched K to position 2, the current was still at its peak and it starts to decrease from there. So when I just closed the circuit, when the circuit is closed, the circuit, when it just got closed, it started from the current 0.1. And obviously 0.1 ampere is bigger than 0.02 ampere. So of course the lamp will illuminate. Of course the lamp will illuminate. Okay, so show that the lamp gives light. It gives light because when the circuit is closed, the current was 0.1 ampere. And I'm using the word was because it started at 0.1 and it will decrease progressively. Okay, so now for the last part, determine the duration of the illumination of the lamp. We have to find the duration. That means we have to find the time. And the only expression that we have in this exercise that has the time, it's the expression, the solution of I2. It's alpha E minus beta T, and I already wrote that here. We already know alpha, it's 0.1, and we already know beta, it's already calculated before starting. Okay, my only problem is with I. What can I replace I2 with? The current that we actually have to replace is the current that the lamp needs to illuminate. So, which is 20 milliamperes. So this is the value we're looking for. So as simple as it is, we write I2 equals alpha, which is 0.1, E minus beta, which is 400T. Okay, and we have to replace I2 by 0.02. Why? Because 20 milliamperes, it's 0.02 ampere. Then we take all the numbers to the other side. We will get 0.02 over 0.1 equals E minus 400T. Then we have to cross out the exponential, so we have to add the logarithmic application on both sides. Okay, but before that, 0.02 over 0.1, this will be 0.2. Okay, then we apply the logarithmic application. You will get log of 0.2 equals log of E minus 400T. Then log and E, they cancel each other out. We will get log of 0.2 equals minus 400T. That to get T, we will be having log of 0.2 over minus 400 equals T, which is supposed to be approximately 4 times 10 to the power minus 3 seconds.